Welcome to this brand new tutorial on getting a intuition to the most famous, the most talked stuff on machine learning, neural networks. Okay, so what is a neural network? Let me you know what, guys, let me just make this thing really quick and simple. Well, I don't know if it's going to be quick, but I just want to give you an intuition to what is going on. And I don't think I'm going to give you a mathematical, totally, like I'm not going to talk in depth, but however, I'm going to give you a small feel for what it is and what you can do with it and whatnot. Let's get started. Okay, so a neural network. Okay, so let me just draw a box here. Okay, don't mind my terrible handwriting. I'm getting used to this tablet. Okay, so I'm going to write this box. Okay, what you're going to do is you're going to provide something to this box and get something out of this box. You can think of it like a gate, maybe. Initially, think of it like a gate box. We'll call this as a gate box. And basically, if you just say supposing you pass in the age of a person, okay, and it outputs the the weight of that person. Okay, so basically all you do is you pass in 23, it outputs 70 kgs. Okay, you pass in 29, it outputs maybe 72 kgs. So it's kind of like think of it like a predictive model. Okay, so basically what is happening inside this box is you are just putting in some inputs. Okay, you're giving in some inputs and it is throwing out certain outputs. Okay, now this box, we can think of this box, we don't know what exactly is happening inside this box, but however, let us try to understand what is going on. And I want to give this box as a reference for understanding the concept of neural networks. Okay, now I'm going to draw a circle. Just imagine I replace this box with a circle. Okay, don't worry about what is going on inside. All I'm doing is providing in some input, and I'm going to call this input. This could be age, this could be color, and it would output probably, you know, just the race of that person. I mean, this looks very racist. I couldn't think of a better option, but however, you just pass in maybe you just pass in the accent of that person. You could pass in anything. You could pass in the audio signal, and it kind of outputs the genre of that audio signal. You pass in the accent of that person, again it outputs the ethnicity of that person. So just think of it like this. So you pass in some sort of input, and these are all your inputs, and the output is coming out, and you exactly do not know what is going on inside this box. And I'm going to take out the terminology, the I'm going to unpeel the terminologies from box to, I'm going to just say perceptron. Just don't worry about what is this fancy term, but right now I'm just going to replace this box with a circle, and it's a perceptron. And basically what is going on is you pass in some sort of input again to the perceptron. The perceptron outputs something else. If you know this, you have got a very basic intuition for what is going on in a neural network. You might ask me, okay, Rakshit, how the hell does this perceptron know that if my age is 23, my weight is 70 kgs? If my age is 29, my age is 72 kgs. Well, you don't have to worry about that. All you have to worry about right now is that this perceptron takes in certain set of input or inputs, and it outputs the values. Okay, so this perceptron is called as a single, let me do this, single neural network. Okay, so as basic as it could get, I am just going to talk what is happening inside the single neural network. How does the single neural network know if my age is 29, the weight is going to be 72 kgs? Well, the answer to that is, let me just change the color of the marker. And so here we go. Oops, why did I choose yellow? Let me choose another one, a darker one. That's cool. Okay, so here we have this setup. Okay, and the setup is the perceptron is here. I'm going to pass in input, and I'm going to call that input from now on as X. Or this is my first input. I'm going to call X1 maybe. Okay, if I have another bunch of, I mean, I can have as many as inputs as possible. Maybe I could pass in the age, and I could also pass in the height of the person. So it then outputs the weight. So it would make more value to pass in the second parameter, right? And in machine learning terminologies, these parameters that you pass in as inputs are called as features. You know that, right? Features. A what's going on? Features, features. Okay. Now, what is a feature? It is basically we'll call it as an attribute. Attribute one, attribute two. Okay. So maybe a person has age as an attribute. Okay. Color as an attribute. Weight as an attribute. And he also has his maybe his accent as an attribute. And you guys know that I have an Indian accent basically. And so you know that basically is these are all called as features, and you pass in features as inputs to perceptron. Okay, and let me just make another x3 here, and here is my output, and I'm going to call the output as y out. Okay, so this y out basically is the output of the perceptron. You know what? Let me just follow the technical terminologies. Let me not just confuse you. Y hat is the output. Okay, so output from the perceptron, y hat p is the output from the perceptron. And basically, all you have to know is that y hat p is going to be something like this. First of all, let me just give you a feel for what is happening in y hat p. But before that, I want to talk about the inputs and something called as weight matrices. I don't know if I spelled it right, um, but however, well, let me just, whatever the spell is, don't worry about that. You guys already know I don't know how to spell. Okay, but okay, so here we go. So weight matrices. For every input, I'm going to attach something called as a weight matrix that you don't have to be worried about right now. For input x1, I'm going to attach w1 as weight matrix. For input x2, I'm going to attach w2 as weight matrix. Input x3, I'm going to attach w3 as my weight matrix. And here I have my output. Now, here is what we're going to talk about. Why do we have a weight matrix? A weight matrix, not matrix, it is matrix. Why do we have a weight matrix for every input? Well, we are going to take a look at that in the next slide. Okay, we just saw right now, let me rewrite that thing real quick. This is my weight matrix 1, and input is coming from here. Weight matrix 2, input is coming from here. Weight matrix 3, and input is coming from here. Okay, oops. Okay, so here is my y hat, the predictions value, and this is my perceptron. Okay, cool. So we were talking about why is a weight matrix included. So now before that, let me just get the value for output first of all. Here, quick. Let me grab my eraser. And parallelly, by the way, I'm training a neural network behind in the background in the same laptop. So that is why it's kind of producing a lot of sound. um, the fan is running real fast. Okay, let me just grab this right here. Oops, what am I doing? Okay, so what is the output y hat? Okay, let me just do something with this right now. And that is I'm going to just do x1 w1. I'm just multiplying my weight matrix with my input, adding it to x2 w2 weight matrix with my input again, x3 w3. Okay, and I'm going to call this as um, z or z. I'm going to call this as z, where z is basically sum of products of inputs and weight matrices. Cool. Okay. I think this is the right spell. Anyway, so that is Z. And Z is basically a way for us to incorporate the input and the weight matrix. And we are trying to incorporate the input weight matrix for all the three possible inputs. And say I had the fourth input, then what would you expect here? I would have just gotten x4, w4. That's it. Now, all I'm going to do is y hat is, I'm going to say sigmoid of z, where sigmoid is called as activation function. Don't worry, don't just freak out looking at all these terms. These are all just fancy terms trying to scare you guys off. But right now, all you have to know is the output of a perceptron. What is the output of a perceptron? It is basically um, a function of z and sigma of z, where sigma is basically the activation function. Sometimes people refer as g, or sometimes people refer as a. They all mean the same. Basically what they're trying to say is output is a function of the activation function with respect to z. That's it. The output of a perceptron is activation function with respect to z. Now that is all there is that we should realize for the output of a perceptron. Okay, now what is basically this activation function? What is an activation function? Why do we need this activation function? Okay, cool. Let me, have you guys come across the sigmoid curve by any chance? Or have you guys come across the tan H curve? Or have you guys come across something called as a rectified linear unit curve? I'm pretty positive you guys are not even knowing what it is. Matter of fact, I didn't even know what it is while I started off, but I'm just trying to, peek at your mind and see if you could kind of recall any of these. Sigmoid, tan H, relu. Well, let us, you know what? Let's get out of PowerPoint right now and let's go out for a second and check out what is meant by a sigmoid curve. Okay, let me. Well, this is my neural network training, and we are going to do this. We are going to do this. It is about time for us to get there. But before that, I want to give you an intuition. So what is a sigmoid curve? Let's take a look at this. Yes, this is what it is. So basically a sigmoid curve is looking something like this. It goes from anywhere from, it has only values. Well, so if you take a look at the equation for sigmoid, this is how it looks. It is basically 1 over 1 plus e to the power minus x. Don't freak out, don't freak out. It is basically, what you're trying to do is you're converting in sigmoid, or basically all these activation functions are basically, do you even recall how many times I've used basically in this video? Oh my goodness. Okay, so activation function, right? Activation function is nothing but it is going to do something called as non-linearity. It is going to introduce non-linearity. Now, why do we need non-linearity in our neural network? So let me get to that point. I'm not trying to give you like a whole, I'm not trying to pump everything at one video, but you should know that non-linearity is required for neural network to learn. This is a new term, but anyway, machine learning is all about learning. Just go with the flow for what I'm going to say now, and then we will unwrap everything. Okay, so non-linearity is required to learn linear and non-linear parts of the inputs. Now don't worry about this. So all you have to know right now is, let me just brief what is going on here. We first took Z as the sum of products of inputs and weight matrices, and then we pass it to an activation function. Okay, and what is an activation function? These are all, I was wondering if you guys know any of these. Even if you don't know any of these, that's all right, perfectly fine. And the point I wanted to make is all these functions are going to introduce non-linearity. Now, non-linearity, why does it have to be present in our neural network? Non-linearity is required because you can basically learn linear and non-linear parts of any input. Now, basically, what is that supposed to mean? Okay, if you know what a linear regression is, basically it is a straight line going between all these set of points, right? This is linear regression. What if, and by the way, all these points are all linear. It is really like you can actually fit a straight line. The whole point about linear regression is that you can fit a straight line. Okay, like, so the linearity means what? Linearity means that you can actually fit a straight line, and a linear regression is basically you take all these points, and there are certain points that you could basically plot on a graph, and very easily you can split all these points into two sections, section 1 and section 2. Okay, and well, this is called linear classification, whatever I'm trying to do. If you divide a straight line into different sections, then it is called linear classification. But what is linear regression? Now, linear regression is basically that, at a given point in X, say this is 10, this is 20, this is 30, okay, this is 5, and here we have, this is definitely not in scale. Don't worry, don't even worry about what is going on here, except that you just have to know, I'm just giving you a really quick intro to linear regression. Okay, so if my value in X is say 7, what is the corresponding value in Y? That is what is called linear regression. Okay, what is the corresponding value in Y? Say this is 8, for example. Okay, if my value in X is 7, my value in Y is 8. And how do I get to know? I fit a straight line, and that's how I get to know. I fit a straight line. How did I fit a straight line? Based on all these underlying points here, okay, and I realize, okay, this is the best straight line I could fit, and based on the straight line I've fitted, if there is a term, fitted, based on the straight line I've fitted, I get the value for y. Okay, now x is a function, y is a function of y, y is a function of x. That is what is the idea behind linear regression basically, and specifically, what is the function? Y is equal to mx plus b, where b is the y-intercept, right? Now I'm not going see where we are going. See, so this is basically linear regression. And why did I even talk about linear regression? I spoke about linear regression because linear classification. Why did I bring up linear regression? I totally even forgot why I brought up linear regression. But however, so this is linear regression. The idea is, yes, so to introduce linearity, you see, this is a linear line. What if my points were like this, where you could not fit. See, my points over here were very straightforward. I could fit a straight line between these 2 points, or I could fit a straight line to find the value for y based on the value of x. But what if my points are scattered like this? Now, where are you going to fit a straight line? At what point are you going to fit a straight line? You can't basically fit a straight line to these set of points. Can you? So look at this. I have 2 classes of points. How are you going to fit a straight line here? And if I want to classify these points, how am I going to classify? So the way I classify that is by fitting something like this. Let me get back here for a second. Draw with purple. Okay. So I'm trying to do my best job trying to separate. So this is class 1 and this is class 2. Now this is definitely not linear, and this is non-linear, right? And if my points are non-linear, then my neural network has to be able to learn, right? And how is it going to be able to learn non-linear points? And that the way we introduce non-linearity in our neural network is by using these activation functions. Yes. So that is what I wanted to get to. I mean, you guys don't have to worry about what is linear regression. You will get to know. If you have not checked out my video, you can check it out as well. And you don't have to worry about what is non-linear linear classification. Let's just say, don't worry about linear classification or non-linear classification. You see, this is what is non-linear classification. And if our inputs, we cannot always expect our inputs to be in a straight line form. In a real world data set, inputs are not definitely in a straight line form. Then how are we going to be able to classify? The way we classify that is through introducing non-linearity. How are you going to introduce non-linearity to your function? How are you going to be able to make it robust? The term is robust. How are you going to be able to make it robust to non-linear inputs? The way you do that is through activation functions. So that is why you need an activation function. Okay, let me so that is why we need an activation function. Okay, let's proceed further. Here we have, let me okay, so now that you know, in a perceptron I have bunch of inputs. Okay, I have the output, and if I have x1, x2, x3 as inputs, and I have w1 as its corresponding weight matrix, w2 as weight matrix, w3 as weight matrix, and y hat is the output of the perceptron. Okay, y hat is essentially what? x1, w1. Well, I'm going to just right now, I'm going to take my eraser quick, and okay, so let me start writing. Whoops. Okay, so this y hat is the output, and that is going to be a sigmoid of w1 x1, well, x1 w1, x2 w2, x3 w3. Okay, and that is the output of the perceptron. And this activation function, there are activation functions, matter of fact, and they are basically sigmoid, tan h, relu. We will see a bunch of them, but you just have to know that these are called activation functions. Okay, great. Now what we are going to do is basically all right. So, but let me ask you this. Let me ask you this. So if my age is, you know what? Let me get rid of this. Let me ask you, how are W1? Okay, so you now know that why do we need? You now know why is it that we need an activation function? Why is it that we need inputs? Obviously, without inputs, you cannot have outputs. But why is it that we need weight matrices? What is the reason, the logic behind why? I mean, introducing weight matrices. Need? Why do we need weight matrices? Come on, guys, think of it. I gave you basic introduction to sigmoid, tan h, relu inputs. Why? And if you guys thought of something, let me ask you this. I'm at a grocery store, okay? All right. Now my bill turns out to be $20. My bill turns out to be $20, and I have say 3 elements that I purchased. Not, well, don't be so technical, Rakshit. Say 3 items that I purchased. Okay. Now my bill turned out to be $20, right? And if I were to take a look at my bill, I see I bought milk for say 3 units of milk. Okay, 3 liters, or and then 3 gallons, whatever. And then I got some fruits for 1 kg. Okay, or let me just make it units. Okay, don't worry about what it is, 3 pounds or 3 kgs. And I also got some vegetables for 2 units of weight. Okay, let's say 2 pounds or 2 kgs, whatever. And here what happened was, for my milk I paid around $12, and I paid around $6 over here, and I paid around $2 for veggies. Okay, now what I'm trying to say is, now if you take a look at this, I have paid effectively. Where is my most money gone to? Where have I paid? I have paid my most money for milk, right? And in my bill, which has the highest weightage in the sense which has the highest bill, or let me ask you this, which has the highest cost? The highest cost is for milk, right? In descending order, if we were to write, the first the most money is spent for milk, the next most money is spent for fruits, and the least money is spent for veggies, right? Oops, let's go back. Why did I press that? Right? And so that is basically what it is in even in neural networks. So if we were to sort of re-engineer reverse engineer this concept to neural networks, what we are trying to do with weights are basically as simple as this. We are basically trying to check out which input has the most weightage. Which input has the most weightage? Okay, we are trying to check with weight matrices. What we are trying to do with weight matrices is, why do we need a weight matrix? We want to see whether the first input has the most weightage, or let me put it in a different way, whether the first input has the most contribution to the output. Which has the most contribution to the output? You know what I'm trying to say, right? So whether the first input has the most contribution or the second input has the most. What did I do? Keep. Oh my goodness, I pressed something stupid. Let me get back. I'm sort of getting used to this. Bear with me, guys. This is definitely going to get better. All right. So what was I trying? I was trying to say which has the most contribution, right? Okay. Which input has the most contribution? Whether the first input or the second input has the most contribution towards the output, or the third input has the most contribution towards the output. So the whole point we are trying to do with our weight matrix is that whether the first one, the second one, or the third one, if I had like 10 inputs, then I'm also going to check for all the remaining 10 inputs as well. So you should know that weight matrix is basically an indicator for your contribution to the output. In statistical terms, it is called how correlated. So basically, we are trying to find what is the most influential factor, which input is the most influential factor, or which input correlates the most to the output. And the way we do that is by adding these weight metrics. Okay, so don't worry, like so basically I'm trying to get you grounded on the concept as simple as possible. And right now you guys all know that y hat is sigmoid of w1 x1 plus w2 x2 plus w3 x3. All right, so now that you know the value for weight metrics, okay, I'm going to talk about I'm going to talk about something called as forward propagation and something called as back propagation. Okay, so what we're trying to do in forward prop and back prop, we should realize that. So here's what we are trying to do. Now, before I do anything, I want to give you sort of an intuition for machine learning. You know what, guys? I'm going to continue this video. I don't think I'm going to talk about everything in one single video. But however, if you guys definitely want me to talk about in one single video, here is the basic intuition for a neural network. So you pass in the inputs. The output is going to be sigmoid of w1 x1. What happened? Okay. Anyway, so you guys pass in and you realize the output is sigmoid of w1 x1 plus w2 x2 plus w3 x3. Okay. Now all you do is you forward propagate. That means you pass in this and you check whether your predicted value. You introduce something called as error, and the error is that you check how good it is. Okay, how good is my model is my model predicting with respect to the real world. Okay, so you check, and sometimes you realize that the error is substantially large. Okay, if the error is substantially large, what you're trying to do is you're trying to minimize the error, right? You will minimize the error, and the way you minimize the error is by doing something called as back propagating. And in back propagation step, what you're going to do is you're going to update the weights. Okay, so once you update the weights, now W1 becomes a better, it gets better and better. W1 gets better, W2 gets better, W3 gets better. And again, we get a better output. Okay, you get a better output. If you get a better output, the error goes down. Error goes down. If the error goes down, what happens? You again, until you get a point where error is almost zero, you back propagate. You again back propagate. Now, if you back propagate again, what happens is, um, again, you update the weights. And as you update the weights, again, what happens is W1, W2, W3 gets better, and your error goes down. You back propagate, error goes down, weight matrices get better and better and better and better. And at some point, your error is almost kind of like close to zero. And that is when your model is almost really good for predictions. So let me you don't have to, like, we are going to write code for each and everything here, but you should definitely know what is going on in a neural network. Let me finalize my thesis, not my thesis. This is there from 1950s. And you know why neural networks are blowing up right now? If it was there in 1950s, why is it that you guys are listening to this? Or why am I talking about this concept in 2017? That is because of explosion of data. Explosion of data has is the major reason why we are now talking about neural networks, because neural networks were ineffective when there were very less data. There was, see, here is the bottom line. In any machine learning algorithm, for that matter, higher the data, the better the accuracy of the model. And the better the accuracy of the model, your predictive outputs are really good. So that's the whole gist. Okay, now in 1950, what happened, they introduced the concept of neural networks, but only in 2010 and beyond was when we started to face the explosion of data. And neural networks are really good, very good, if you provide them with exhaustive amounts of data. And that is what we are right now experiencing. I mean, you know what, guys? From the time you started watching this video until the time, matter of fact, until right now as well, the amount of data the internet has created right now can leave you exploring for the rest of your life. You could kind of explore, play with the data for the rest of your life, only between the data that was generated from the starting point of this video till right now. And don't you think it's amazing and insane equally? Well, that's what I think, and that is why machine learning engineers and enthusiasts have realized the potential for neural networks, and that is what is the reason for explosion of neural networks. However, so here is what our thing is. Okay, we first get the first output, and the first output is, I don't want to write that equation again. You know it. Sigmoid of W1 x1, W2 x2, W3 x3, and then you check for errors. Check how bad is the model. Check for error. Okay, and then what you do is you back propagate. Now, once you do this back propagation process, you update the weights. Weights get updated. And once you update the weights, okay, now your model gets better. Again, you get a better output. Okay, this is an iterative process. That means you keep doing it over and over and over again, as long as error is almost close to zero. As long as ideally it's very hard to get to zero, but we want to minimize the error, or let me just put it in this way: minimize the error. Okay, so that's the whole concept of neural network. You first get the output, and the output, you know what, let me just write it finally. Sigmoid of w1 x1 plus w2 x2. This concept of w1 x1 is called as forward propagation. Okay, don't be worried about what is forward propagation. This is all it is. You just do forward propagation w3 x3. Okay, and then you check for what is the error, and then you back propagate, and then you update the weights, and you sort of do this process again. Once you update the weights, go back, and basically you get the output by forward propagating, right? And you check for error, you back propagate, update the weights. It's like a very it's very simple, guys. Okay, all I'm going to do is just, this is not okay. So here is what it is, and you do this process for the entire training set. How long do you do this? You do this process until A, you minimize the error, until B, you finish the data points. That is, you finish data points. What is data points? I'll explain that. You basically finish. My goodness. Where is the slideshow thingy? Okay, I have to go from beginning. You guys have to help me out in the comments, because I haven't used this much, and I'm finding it really hard now. Anyway, so while there are no data points, as long as you finish the data points, or you finish the error, minimize the error. I mean, basically the first importance is to finish the data points. Okay, I'll explain what is meant by finishing data points in a second, but this is how it goes. You first train. Finish data points means what? Train. You finish the train. You first train the neural network, and how you do that? As long as there are no data points, you do forward propagation. Where is my mouse? Okay, you do basically a forward prop. Okay, once you do forward prop, you know what is forward prop now. This is what is forward prop, and then you check for error, you minimize the error, you back propagate. In back propagate, what happens is you update the weights. Update weights. Okay, and that's it, and you repeat this cycle over and over and over again until the error is going to almost close to be equal to zero, and you have exhausted all data points. Sometimes error will not be equal to zero. Okay, error will not be equal to zero, and in that case it's okay, no worries, but you should have exhausted your training points. What is meant by exhausting my training points? Let me explain that, and we'll wrap up this neural network intuition tutorial. Okay, so now let me just say I have, let's just say I have age, I have weight, and I want to be able to predict my, well, I have height, I want to be able to predict my weight. Okay, so I went to, like, let's just say 70,000 people. I asked each one of them, hey, what is your age? He says, my age is 23. My height is 5'9". Okay, obviously. Um, and my weight is, say, let's just use 70 kgs. Okay. Okay, my age is 46. My height is 55.3, and my weight is 55 kgs. Okay, and I went to some random dude, and he just said, I'm 99, my height is 6'7", and he is just weighing 117 kgs. Don't you think it's really cool? At 99, weighing 117 kgs, I just think it's really cool. Well, I hope there is someone like this. But however, so these are all my data points. You see, these are all, this is called as my target label, and this is what I'm trying to predict. This is what I'm trying to predict, and these are all my inputs. So this is my x1, this is my x2, this is my weight, that is my weight is y. Okay, basically you should always remember y hat is the predicted output in the sense the output coming from a neural network, and y is the output from basically my neural network. Wait. Output from my data points. I'm sorry. What did I just say? Data points. Whoops. Okay. Y is the actual, or in other words, actual output. Okay. And y hat is my predicted output. Okay. So sometimes the predicted, this weight thingy, whatever you're trying to predict is would be called as target. Just be aware of that as well. And I proceed further. I have so these were my 3 data points, right? And I go on and go on and go on until I reach my 70,000 data points, and that is what is called, until I finish, this is called as exhausting my data points, and I feed all these data points to my neural network. Well, I just talked about perceptron, right? Let me show you a neural network, and then I'll wrap up this video. See, every topic is just getting added up again and again whenever I want to finish the video. However, so this is called as exhausting my data points. I have 70,000 points. I fed every single point to my neural network, and that is what is called as exhausting my points. And I keep on doing that process until you remember those processes that I showed you: back propagate, forward propagate. See, forward propagate, check for error, minimize the error, back propagate, and then you update the weights. As long as you've exhausted data points, that is what I meant. So I train, or I give out all my 70,000 points to my neural network. By now my neural network would be really cool at predicting somebody's weight given their age and height. You see, that is what it is for basically how this is what happens internally. I have not spoken about mathematics yet. I am going to do that, but you should know this is how a neural network works. But before that, I just talked about a perceptron, right? A perceptron is basically one having just one unit that performs sigmoid of w1 x1 w2 x2. You know that, right? This is x1 w1, x2 w2, x3 w3. But right now I'm going to show you. Now if I like stack up a bunch of perceptrons, like if I stack up something like this, a bunch of perceptrons. Now this becomes my neural network, and this is called as a shallow neural network. Okay, and shallow neural network, and this is called as a deep neural network because every perceptron is connected to every other perceptron. So don't forget, this is my perceptron connections. Every perceptron is connected to every other perceptron, and that is what is called as x1 x2. Okay, so w1 w2, and I keep doing this. Let me you know what, Let me show you a picture of a deep neural network and we'll be done. Deep. So this is how it looks like. You see, these are all the, so this is called as an input layer. This is the hidden layer, hidden layer, hidden layer, output layer. So this is what it is. A bunch of perceptrons connected mutually to every other perceptron. So this one is connected to this, all the layers. This input perceptron is connected to every other layer, and you keep on doing this forever, and that is what is called as a deep neural network. And the reason why we do that is obviously it gets a really good good prediction. And um, and my figure here is kind of the same, where I could just make it as input layer here. This would have been my input layer, okay, and this is my hidden layer, and this is my output layer. All right, so that is what is the basic intuition for neural network, and I hope you guys like this video. If you like this video, give it a thumbs up, subscribe, and share, because I'm going to just keep out more content. And smash that like button if you just really like this explanation. And yeah, I mean, that should be it for neural network intuition. All you have to remember right now is this part where you keep doing it. You first do forward propagation, check for error, back propagate, update the weights and output. And then you repeat the same thing. You forward propagate, check error, back propagate, update weight. Okay. Oh yeah, oh my goodness. Did I talk about bias? No? Okay, guys. This is really important. So this is my perceptron, right? Bias. Okay, how could I forget this? So this is my perceptron. This is my input x1. It has a output weight matrix w2, x2, and w3, x3. And I'm going to deliberately do something here. This is my output y hat, and this is my z function. What is z? It is basically w1 x1 plus w2 x2 plus w3 x3, right? Additionally, I add a bias function. I add a bias function. I add a bias to all the inputs here, and that is going to be my bias. You should always add a bias, otherwise your output is not going to be all that great. So the point behind adding a bias is you sort of add like a correction for the weight metrics, weight matrices. I'm sorry, weight matrices. Okay. So this bias thingy is basically, let me. How could I forget that, guys? Just don't miss out on the bias. You should always add a bias, and it's kind of like a correction to weights. We'll understand that in the next videos, but you should always remember that bias is added as a correction to weights. Okay, and I am going to just show you. So take a look at this one really quick. So bias allows you to shift the activation function to the left or to the right. See, that's a correction. And if you it kind of now if you guys know this, right? You guys know, let me, whoa, it's training super hard, and that's why it is kind of like getting stuck in between. Anyway, you guys know this, right? Y equals mx plus b. Why is b added here in this equation? B is added because it sort of aligns the line here, right? This is b, right? If b is 3, then it goes from here. If b is 5, the line goes like this. you I mean, the point I wanted to make is it kind of is like a correction to the line's inclination, and that is what is this bias term. Pretty much the same. It has the same role even in our neural network. So don't you guys forget to add the bias, and I hope this video makes sense to you, gave you a really good intuition to the concept of neural networks, and that should be it. Thank you guys. Click on that subscribe button.